Hello, Algebra 2 students. Glad you were able to find a little bit of time to help review yourself for your test for Thursday. Again, I apologize for us not having a designated review day, but I found it better to cut out the review day and get the test in before spring break rather than have you take a week and a half off and then come back and then have a test following spring break. Anyway, obviously we have an entire unit dealing with the rational functions and the equations and the graphs of them. So let's see if we can't review real quick and find a little bit of information out. Now, we discussed at the very beginning, a rational function is basically an expression of a ratio. Okay, so we end up with variables in the numerator, variables in the denominator. Now, we've looked at specific types of rational functions, but the term rational simply means that we have polynomials, polynomial divided by another polynomial. There were only two requirements for the rational function, and one of them is that the degree of the denominator must be at least 1, and of course degree means the highest exponent, so that means there's going to be a variable in the denominator, and of course our denominator must not be allowed to equal 0, and as we learn moving through the unit, when the denominator does equal 0, it causes a vertical asymptote. So it's not like it wrecks the entire problem. It simply means that an asymptote has arrived and the graph does not exist at that location. Okay, so the parent rational function is simply y equals the reciprocal of x. And we've learned several things about it. Of course, the parent function is centered at 0, 0. And keep in mind, the center of a parent rational function is not actually part of the graph. It is the center, kind of like the anchor for the function. Okay, but the center does not actually exist as part of the graph. And the parent function in its regular positioning, the hyperbola that is graphed, it exists in the first quadrant and the third quadrant. Okay. Now we've talked about the asymptotes quite a bit that go along with the rational function, and of course when it comes down to the rational function, we have two asymptotes that pass through that center location of the hyperbola, one going vertically and one going horizontally. And of course keep in mind, for a vertical line like the asymptote, the yellow one that's in the picture, okay, a vertical line has an equation x equals, and then the number that you put on that is where does it cross the x-axis. And a horizontal asymptote, like the red one that you see there, it has an equation of y equals, and then a number that tells where it crosses the y-axis. Okay, so the horizontal and vertical asymptotes pass through the center. If you can find the center, then you have the information that you need for the equations as well, looking at h, comma, k. Okay, we've also talked about the domain and range. We should have seen plenty of times by now that with the rational function, our domain and our range is actually broken into two intervals, and that's why we have those asymptotes there, because the graph or the domain cannot cross over the center point because of that break, that asymptote that's in there. So you actually get the domain coming from negative infinity up to the center, and then from the other side of the center off to positive infinity. And to get the same type of explanation and argument when you're talking about the range will come up from negative infinity, it will reach the center, and there will be a break right there. That's why we have that horizontal asymptote, and then the range will continue on the other side of the center off to positive infinity. So you get two different intervals for domain and two different intervals for range when we're dealing with our rational functions. We haven't talked about it a whole lot, but of course the inverse is always a possibility with any equation. And one of the rare instances in all mathematics is the inverse of the parent rational function is actually the same as the parent function itself. Okay, so we have a situation where the function and its inverse, or the function is its own inverse. Now this is of course on the parent function. When you start moving these equations around in the graph, then obviously you do not get the exact same inverse because the graph has been translated. The next day we came back and started talking about the equations a little bit. Okay. And we saw that the adjustments that were being made to the equations of the parent function for the rational function, very much the same type of rationale that we had with the square root function last unit. We still have h comma k as our center of our graph, and h is still is attached directly to x, and k is positioned so that it can directly affect y. And of course, remember that, like in the case over there on the right side in the center of the screen, where you have x minus h in your denominator, remember that that minus is built into the formula. So if you are looking at an equation where it does not say x minus some number, then the only explanation for that is that h must be a negative value, and the back-to-back negatives between the formula and the value canceled each other out and made it look positive. And as we move our graphs around, as h comma k moves around in the graph, of course the asymptotes are going to move with it. So some of you are still kind of under the impression that the asymptotes always live on the x-axis and always live on the y-axis, and that is not true. It moves with the center of the hyperbola. Now we saw that the value of the coefficients in the numerator and in the denominator can change the speed of the graph. Okay, so what you need to do is you need to read your coefficient in the numerator, read your coefficient in the denominator. Together, they make a single value. As that value becomes smaller than 1, then the hyperbola is pulled inward towards the center. If a is 1, that is the normal speed of the hyperbola, and as a is greater than 1, then the hyperbola is pushed further away from its center. If you reverse the sign of a, either by way of changing the sign in the numerator or changing the sign in the denominator or just changing the sign of the fraction, that reverses the direction of your variables. Okay, and what we saw on this one is it does not matter whether it is the y value that is reversed or the x value that is reversed. What we saw was that the graph was basically flipped, in the sense that instead of being in quadrant 1 and quadrant 3 away from its center, it moved into quadrants 2 and 4 away from its center. Okay, so we worked several examples on how to read those, so you might want to watch back through those videos if you need some help on how to build the graphs. Okay, so after looking at the equations and how to build the graphs from them, we reversed the process and came back and said, okay, let's see if we can't get the equations assembled based upon what we're seeing in the graphs. Okay, well, it's basically the exact same information, just a different way of thinking about it. So we still have the graphs, we still have the equations, and of course understanding the parent function and how it moves and where it's positioned and what direction it goes, that becomes the key to being able to understand what the equations ought to be able to, or what the equations ought to say. Okay, so one of the things that we talked about is the fact it's the coefficient, the a term, that is the part that is the most difficult piece of information to read. Okay, so as a changes, it's important to know what the parent function should have done. So what we did is we spent a little bit of time in saying, okay, from the center of the graph, we're going to start taking some steps away from the center. So as x changes, 1 step in either direction, 2 steps in either direction, 3 steps in either direction, it's important to know what the y value is doing as you move by those step sizes. So as x moved 1 step either direction, the parent function changed y 1 unit up or down, and as x changed 2 steps in either direction, then y was actually only plus or minus half a step. As x moved 3 steps away from its center, then the y value actually only moved 1/3 of a step away from its center, and that makes perfect sense when you get to thinking about the parent function is the reciprocal of x. So as x is moving 1/1, the reciprocal of that is still 1/1. As x moves 2/1, the reciprocal of that is 1/2. As x moves 3/1, the reciprocal is 1/3. Okay, so that's where those step sizes are coming from, and that becomes kind of the basis for how to decide if the speed has been changed and by how much it's been changed by. Okay, so we worked through several examples in the notes, so pull that video back up if you need help on that. And then the last thing was to look at the inequalities. And of course, what we saw, of course, is you have the shaded area within the graph Okay, because with inequalities, it's not just being on the graph that's the goal, it's being in a particular area with respect to the graph. And one of the things that we notice quite obviously right off the bat is when it comes time to shade our graphs, well, there's two different curves in a hyperbola. Okay, so an inequality will mean shading a particular direction from both of those curves, not just only one curve, which is what we've seen with many of our graphs in the past. Okay, so we talked about the basic strategy again. Okay, if a variable is already isolated, an inequality is very easy to read. If it says y is less than the equation or the graph, then you shade to where y is smaller. That's downward. If the equation says y is larger than some graph, then you go to where the y values are larger. You shade upward. Same thing if it happens to be inversed. If it says x is smaller than the graph, then shade to the left because that's where the smaller values of x are. And if it says x is larger, then we shade to the right because that's where the largest values of x are. Okay, so if the variable is isolated, it's very easy to read an inequality. If the variable is not isolated, you can isolate it, assuming you're comfortable doing that, moving some values around. And once your variable is isolated, then you can shade from there. And the fail-safe kind of catch-all method is if no matter what, you can pick a point in open space and you can plug it into your inequality. If the inequality agrees with that point, in other words, it gives you a true statement, then that means the inequality likes that point. Shade toward it. If you pick a point and plug it in and you end up with a false statement in that inequality, then that means the inequality does not like that point. Do not shade towards it. Okay. If you pick a bad point, meaning maybe a point that is on one of the asymptotes, then you're going to end up with a fraction in your, when you plug into your inequality, you're going to get a fraction that's undefined, and you won't be able to decide whether the equation likes that point or not, because a fraction that has 0 in the denominator has no value. We don't understand what that means. So pick a better point, plug it in, and go from there. The rest of that was just examples, so you can look back at that video if you need more examples on that. Okay, that's pretty much what we're facing. Of course, there's always the possibility, like on the last test, that we may see a bunch of stated problems or word problems, things like that. But the one thing that they will all have in common is, of course, they will be rational functions of some kind. And basically the lowdown on that is as one variable changes one direction, the other variable changes in a different direction. That's where that reciprocal relationship comes into play. Okay, so do not restrict your studies or your thoughts to only the lessons that we've covered. Also think about the possibility there may be some word problems. So if you feel like you need some more help on that, of course, come in. The assignment that we worked on today, you need to get that completed. And if you feel like you need more problems than even that, I bet you can Google just about any number of problems that you would like on rational functions. Okay, so hopefully that'll help you get a little bit better prepared. I do appreciate you finding time to do some studying, and I hope everything goes well for you at the test.